Hey y'all, let's cover exponential functions guided notes. This video is only going to cover through example 16. I think it's number 5 on here. Just to start off, we're only going to be covering section 4.5 from the textbook. And I provide you that information. So when you click on your student guided notes, you can click on this just to go straight to the textbook for this. But for pages 8 through 16, it's a little bit blurry. All right, so we have only up to this point been talking about linear growth, linear functions. So we had a constant rate of change. Sometimes we had an initial value. Sometimes we didn't. That's our B. We didn't always have a slope or a constant rate of change, and if we didn't, that's a horizontal line. So if we had an example of f of x is equal to 3x plus 4, the slope or the constant rate of change is 3, and it's increasing by 3. So it tells us that the output increases by 3 each time the input of x increases by 1. All right, so to see the difference between companies A and B, I'm going to create a chart down here, which I did this in class. This is for folks who missed it or need to go over it again. Company A has 100 stores and is opening 50 new stores per year. Okay, so I'm just going to deal with company A right now. And we're going to look to see what the growth looks like for 3 years. So company A starts off with 100. That's their initial value, their B, and they are adding 50 new stores per year. So 100 is the starting plus the 50 new ones. So after year 1, they have 150 stores. Year 2, they start off with 150 and they add another 50. So then they have 200 stores at the end of year 2. Finally, for year 3, they start off with 200 stores. They add another 50. So that's 250 stores they end up with at the end of year 3. Okay, let's talk about company B. Company B is not growing by linear numbers, by a specific number per year. They're growing by percentage. When you see something growing by percentage, that is going to be exponential growth, or if it's decreasing by a percentage. So this one is linear, and this one's going to be exponential. And we're going to see the difference between the two. So company B is increasing by 50% of their total each year. They start off with 100 as well. So for percentages, it's 100 times, well, there's a couple different ways I can do this. In class, I end up showing you a formula for it. So I'm going to show you something different instead. So it's 100 plus 50% of that 100. So 50% of means times 100. All right, we can't just willy-nilly multiply by percentage. We have to change that to a decimal so that we can actually multiply it and use it in this formula. So 100 plus, when you change from a percent to a decimal, from a percent to a decimal, you have to divide that percent by 100. So divide by 100, and you get rid of the percent. So it becomes 0.5 times 100, which is 50. 100 plus 50 is 150 stores after year 1. Okay. Now, year 2, it's going to start off with the initial amount of the number of stores we had at the end of year 1. So we're starting off with 150 stores, and we're going to add 50% of that 150. So I'm going to go ahead and use the 0.5 that we've already calculated times 150, and I get 150 plus, well, I'm just going to multiply 0.5 times 150, and I should get 75, and I did. So instead of 50 stores opening in year 1, they have 75 stores opening in year 2. So that becomes 225 stores in year 2. So they're already beating out company A. So you should already understand that exponential growth is going to grow faster than linear growth just by this example. And it's going to always be that way. So exponential will always beat out linear as far as growth, or so as far as increasing or decreasing. How's that? All right, so let's go to year 3 and finish this out. 225 plus 50% of 225. So that's 225 plus, I think it's 30, I don't know what it is. So that's 225 times 0.5 is 112.5. So that's 237.5 stores. Now, for a conversation on this, maybe the 0.5 is they're halfway through building another store. So if I asked you, how many stores did they build, did company B build in 3 years? You're not going to tell me company B store built 237.5 stores. That's just not how we talk. You're going to say they either built 237 or 238. So did they build 238 stores in those 3 years? No, they didn't. Yes, I know you want to round that up. And yes, you could if it's talking about something else. But stores are either all or nothing. It's kind of like people. You can't have half of a person. Well, I guess you could. But in discussions, we should say that at the end of year 3, company B has 237 stores, just to understand that. But the math is right. All right. From this, we can generalize, noticing that to show a 50% increase each year, we multiply by a factor of, now they want me to use just the plus sign, and I don't like to do that just because it tends to get confusing because students don't understand that you can use a minus sign in there as well. So for this, for company B, I would say that they started off with 100 stores, and then it's 1 plus or minus the rate, which is 50%. So this is an R, which would be our 0.5 to a number, okay, to each year. So in the equation, the initial quality, oh, we're not doing that. All right, so hold up. So we're going to do B of N. I'm going to use my F of X. F of X is equal to A 1 plus or minus R to the X. This is my formula that I like to use for exponential growth. A is our initial quantity, which in this case would be 100. So we're using B of N, which is fine. And then 1, all right, it's growing. So because it's growing, we're going to use plus the rate, which is 0.5 to the X. And theirs is an N, actually. So it's 100 and it's 1.05 to the N. So their growth rate is 1.05, or no, it's 1.5. It's there's not a 0 there, 1.5. So sorry. 1.5 is their growth rate. Generalizing further, we arrive at the general form of the exponential function, and that's where we move on to the next page. All right. So exponential growth, just to show y'all, and I kind of did this in class as well. If you're looking at a linear function, it's going to be growing at a constant rate of change. It's just a straight line. All right, this is linear. Not giving you any numbers in regards to, but just to show that linear is going this way, exponential is going to go up much faster than linear is. And we proved that in the table that we just completed. All right. Exponential growth or decay. So when we're talking about linear functions, we're talking about, is it increasing or is it decreasing? Those are the words I want you to use when you're explaining or interpreting what's happening in a linear function. All right. With an exponential function, increasing is referred to as growth and decreasing is referred to as decay. So you need to understand the terminology for those. Decay will shrink what's happening, and the growth will increase or grow. All right. So I don't like this at all, I like to use these right here, growth and decay. So make sure that you have these on your note card. You can have a 3x5 note card, one side of it for your exam. All right, to where A is the initial amount. So the initial or starting amount is A. R is your percentage in decimal form. R is your percent in decimal form. Like we took the 50%, we changed it to 0.5. And then X is the time. It has to do with time in years. It's always, X is always time in years. Okay. You're going to need that when we get a little bit further into one of the later videos that I make on this. All right, so let's complete this table. We've got an initial, we've got a function, initial value, growth or decay, and then what is the rate? All right, I'm going to give you a couple more formulas here to help you out with this. Initial growth is just our, I'm going to write it here, f of x is equal to a, 1 plus or minus r to the x. So a is my initial value, so that's 430. To know whether or not something is growing or decaying, if it is 1 or greater inside this parenthesis, all right, that means we have growth. Because the number inside the parenthesis is 1 or greater, that is growth. Pardon me. We'll talk about decay here in just a second. The rate, to find rate, all you need to know is that you have growth. And if you have growth, you're going to use this formula. You're going to go, you're going to write the number inside the parenthesis, 1.15. You're going to subtract 1. And then you're going to take that decimal and change it to a percent. To change from a percent to a decimal, I told you earlier, you divide by 100 to go from percent to decimal. To go from decimal to percent, you do the opposite or inverse of division, which is multiplication. And we're just going to multiply that by 100. And we're going to write 115. I'm sorry. It's just 15%. There we go. Today. All right, that's growth. That's how you handle growth. Decay is a different beast. So, which we haven't talked about yet. Let's start with initial value is 23. It's just the number in front of the parenthesis. If there's no number in front of that parenthesis, remember that it's 1. It can't be 0 because then there would be no parenthesis, because anything times 0 is 0. So our initial value is 23. We have decay because it is less than 1. The number inside of the parentheses, if it is less than 1, you have decay. Okay, so that means that initial value 23 is going down. It's decaying, it's decreasing. All right, decay is different. Here, this is our growth, how to handle it. Decay, we have to take 1 minus what's in the parentheses. For growth, you subtract 1 from what's in the parentheses. Decay, you go 1 minus what's in the parentheses, which is 0.8. So we get 0.2. Once we get the decimal, we're going to switch that to a percentage, same way, by multiplying by 100. And I get 20%. Okay? Do not forget to multiply by 100. That's the big thing that people forget. All right, the next one is they're wanting us to create a function given the initial value, growth or decay, and the rate. So let's get through this. The function, I'm just going to use f of x for both of these. My initial value is 1.87. I'm going to handle them one at a time. And it's going to be to the x. I can't forget my exponential. All right. I've got that taken care of. It's growth. So growth is 1 plus r. All right. So that's going to be 1 plus whatever this percentage is as a decimal. All right. So it's going to be 1 plus, not 5%, but 5 divided by 100 is 0.05. So that's 1 plus 0.05 is 1.05. Okay. When you have growth, you're going to take the percent, 5%, you're going to change it to a decimal, and then you're going to, because it's growth, you're going to go 1 plus that number. 1 plus 0.05 is 1.05. That's how you get your growth. Decay is the same thing, but instead of 1 plus R, we're going to use 1 minus R. Let's start off with our initial value, 52. Get our X up there. Decay at 10%, we have to take that 10% divided by 100 to get the decimal. Now it's 1 minus R because it's decay. So 1 minus 0.1 is 0.9, and that's what goes inside of the parenthesis. Okay. I think that's it for that one. Is that correct? 1 minus 0.1. Just to make sure my math is correct here, just because I'm worried. Okay. All right, good. All right, example 16, and then I'm going to end this video and we'll move on to another one. T of Q represents the total number of Android smartphone contracts. So we're going to have to interpret something. So I need to know what all these words mean. In the thousands, this is the part that kicks everybody's tuchus. It's held by a certain Verizon store region measured in Q quarters since January 1st, 2010. All right, that's what the Q means. Interpret all the parts of the equation. So we've got T of Q, but instead we have T of 2. All right. What does that mean to begin with? Well, Q is the quarters since January 1st, 2010. Okay. And this is 2. So this is the second quarter since January 1st, 2010. All right. So in the second quarter, what's the next? We've got 86 is an initial value because remember f of x is equal to a 1 plus or minus r to the x. So a is our initial value. The Verizon store started with, because it's the initial amount, started with what? What are we talking about? What is this T of Q? T of Q is the total number of Android smartphone contracts. So the Verizon store started with 86 in the thousands. So 86 times 1,000, 86,000 smartphone contracts. Okay. 1 plus 1.64 means we have growth because it's greater than 1. So the contracts are growing. So how can we say this? At a percentage. So the contracts, we'll just say it, contracts are growing. Sounds kind of funny. At some percentage. How can we figure that out? We've got 1.64 inside there, so we know it's growth. So to find out what that percentage is, I'm going to take that 1.64 and subtract 1. And I get 0.64 that I need to multiply by 100 to get my percent, which is 64%. Contracts are growing at 64% and end the quarter with how many contracts? 231.3056. But remember, this is all measured in the thousands. So we have to take that number and multiply by 1,000 to get our answer, with 231,305.6 contracts and end the quarter with 231,305.6 contracts. That is interpreting all parts of this. You will have to do this both in your homework as well as on your exam. Okay, get comfortable with it. Use the words that they have. All right, that's it for this video. I'll see y'all back on the next one.